Okay, let's begin. Today I promised you a small overview because you asked how all these different lectures we had so far in the course are connected between them. So we decided to slow down a bit and try to focus more on understanding what we've already seen rather than giving you more and more information. But in the end, we'll end up with a new topic, which is the next step. So far, we have reached all about how SimCLR works and this loss function and the batch size and the correspondence to negative samples. And I will go one step beyond that and see how the state-of-the-art methods the latest year do self-supervised representation learning on the visual domain, but without being dependent on the batch size nor the negative samples. So the first part, some credits. This presentation is based from some, partially on some slides from a CVPR workshop from Spiros Gidais and Andrei Gursuk. So we'll begin with a small overview of the self-supervised methods we have seen so far in Vision. So we saw the pretext task of autoencoding, denoising specifically autoencoders. So we have the data, we add some noise, and then we try to reconstruct the initial image. So the intuition was that this intermediate representation between the encoder and the decoder, which is called bottleneck representation or intermediate representation, will help us, we'll learn some underlying compressed version of the data, and we can use this as a downstream task. Even though the concept looks decent, in practice it's very hard to learn any important and relevant representation for different downstream tasks. Why? Because we cannot guarantee that the model will focus on the high-level information, or otherwise called the semantics, which is task dependent. For image classification, it's the class. So here the digit. So it's very hard for the model to distinguish between what is the actual noise in the data and what is the signal. And as it's shown in the slides, we say that low-level statistics or cues are sufficient to distinguish between these tasks and reconstruct the digit. Okay, then we switch to more hard tasks. So we saw colorization and the generative task of predicting the actual values of some parts of the image with in painting, or you can find it as in painting. So here we ask for the model to do a much harder task, a generative task. So we remove some part of the information and then we are trying to predict this information. On images we predict like a square or any mask based on the image. And we saw that the L2 reconstruction loss, so the mean square error, is always producing, it's not even performing well on the generative task itself. It's produced these blurry predictions. And then I presented some methods with generative adversarial networks and additional loss functions where you can make the predictions more realistic. But it doesn't guarantee anything related to the relative features that we will learn for this task. And most importantly, we ask the model a very hard task with a lot of useless details regarding predictive learning, like regarding the next step would be the downstream task. We use these representations. But these representations have a lot of useless details. So the model needs to extract color, boundaries, and all this stuff. But for the downstream task, we don't really care about this. This is a generative task. So these methods were initially proposed but never really applied in a big scale. Why? because the underlying learned features do not correspond to any understanding of the image. So far so good, any questions? Then we say, okay, let's apply some transformation and try to predict this transformation. We saw the best one with a wider applicability was this rotation prediction task from 2018. You also implement this in the exercise. So the intuition here is again that we learn to recognize some high-level concepts like nose, eyes, heads, but also there is no guarantee, there is no theory behind it, there is no information that this will lead to actual image understanding. And for random images on the wild, maybe this rotation doesn't even make sense. You can think of an image with an orange, for example, with a sliced orange. No matter if you rotate it and you can predict the rotation, it doesn't mean that you learn anything about the orange. So there are a lot of counterintuitive examples. So then we delve a little bit in the information theory and how we can approximate maximizing the mutual information between two views, or a lower bound of mutual information, which we saw that this contrastive loss, or n extent, is like one objective that pushes together a pair. So instead of trying to come up with different tasks, we create pairs. Okay, pairs. How do we create the pairs? We take views, we take the image, this elephant for example, and we create two different views by applying different stochastic transformations. We saw that in this regard, cropping and jittering are the most important transformations. So we move to the pair level, and then we play with the, basically in the feature space, so in the output of the encoder, we have all of those features coming from positive pairs, so views from the same image, and then we try to pull them together. And we saw that this results in a feature space that all the images are uniformly distributed, much more than in the supervised case. And in parallel, that the views from the same image are pretty much aligned in the feature space. So the views from the same image, after training this model for quite many epochs, these features are aligned in the feature space, the positive pairs. So the views from the augmentations of the same image. So what is the limitation? We saw a lot of limitations regarding the batch size and the negative samples, where we saw different techniques to come up with solutions like this momentum encoder approach, where you have this this dynamic dictionary with small batch sizes. All right. So the problem here, as it is shown on the red here, is impossible to know it's very hard to define the negatives. We randomly sample the images in the batch or in the queue, but we cannot actually guarantee that these images are negative. Why? Because we don't have the human annotated information to tell explicitly tell us that you should push away this pair of views of a dog with respect to all the images that don't have this label, like cats or airplanes or trucks. Okay, we saw this part. Then we touched upon another topic, which is knowledge distillation. So this seems a completely different direction from the last lecture, and I can definitely understand why. So what is knowledge distillation? We have at least one model. If we have one, it's usually a big model, and we have and we try to distill this model to transfer the knowledge of this one model into either to usually one smaller one. either if we have like one big model, or as we call it, an ensemble, so a collection of different models. And we're trying to transfer this information to one single model. So this seems completely distant in the beginning from what we saw in how it is related to contrastive learning. We saw 4 different approaches. I won't go too much in depth. So the first equation is from Hinton, which basically takes the cross entropy between the real labels and the soft targets, which are the predictions from the teacher model with different temperature and different weights. And then the second one is what we did in the exercise. We opted for KL divergence with the soft targets, with different weights between cross entropy from the real labels and KL divergence from the pre-trained teacher. So this is the most general and simple way to use knowledge distillation, given a pre-trained teacher with a head that outputs the number of classes that we want. Then we saw that we can also do contrastive learning even with one or multiple teachers. So instead of having views like augmentations of the same image, we now use let's say the teacher and the student, and we push their features together on the feature space. This can be implemented with one or multiple teachers. So it's again the exact same objective, contrastive learning, but now we don't push together views from the same image, but the representation from the student and the teacher, or multiple teachers, and then we just sum them up. The third was really the 2 latest approaches that I saw. We will not focus in depth at the moment. It's just that I want to re-emphasize that it's particular to vision transformers, where they find out this finding that you don't take the soft targets, so output of the teacher plus softmax. You also take you only take the argmax, so the unfolding distribution, that is the output from the teacher. Again with a supervised pre-trained teacher. And the last one, we will see this like more closer to the latest state-of-the-art self-supervised learning, but for the moment we will not focus on that. It's just called mass image modeling, and we'll see it in depth in the next lectures. It's also related specifically to vision transformers. Alright, so now we have these 2 initially unrelated topics, and I will try to bring them together. Self-supervised learning and knowledge distillation. Yes?
Just last before the one before. Yeah, this one. The model sizes are the same. Then why
yes.
It's like taking average, right? There is nothing. Is there a special thing about this student? Because if the model size is the same, it's just another network trained with different.
If we have
decided parameters.
Yes, if we have one teacher, it's typically a bigger teacher. Otherwise, if student and teacher it's exactly the same network, we have seen that by simply taking multiple random initialization from the same model and train it for n times, you get a significant improvement on your data, and then you want to transfer this improvement to one single model, so that during inference, instead of having to process this image n times, or as many teachers as you have, and then take the average, you pass this information to the student. Any other question regarding knowledge distillation? Okay. So let's try to imagine. Let's try to draw some connections between knowledge distillation and self-supervised learning. So knowledge distillation assumes that there is a pre-trained teacher, either supervised trained or self-supervised trained. and we take this contrastive loss. But let's say in the beginning, supervised, pre-trained teacher is there, and we try to pass this information from the teacher to the student. That's why the sizes here are different, so the teacher looks bigger. And we saw these different loss functions and approaches with cross entropy from the soft targets or KL divergence. And then you have to balance between the two loss functions. Another thing is that the input to both models is the same, either if we use augmentations or without augmentations. So both models see exactly the same image information in general. The student is typically smaller, and student surpasses teacher. This would be the ideal case, but it's not really happening, just ignore this part. So now, let's go to self-supervised learning. So here, we haven't talked about any specific approach, but we will. But here we assume that there is no access to a pre-trained model, so there is no teacher to begin with. But we will, our purpose will try to create a teacher in parallel with the student. This is what we saw, what was happening with this exponential moving average, if you remember. So this is the very important principle of self-supervised learning without negative samples. And here, the student and the teacher have access to different information. So the teacher has an advantage because it typically sees a larger part of the information, even if they have like different stochastic transformations, different augmentations. The teacher typically sees more of the image, so it can be more confident and has more information to predict what the actual output should be. And by working on, by iteratively having a slightly better teacher, the student improves. And then there is this dynamic that the teacher improves a bit because the teacher is an exponential moving average of the student, and then the student also improves. So we try to create this dynamic where both models are improving through training, even though they have the same size. So now, what we're going to do next, we ignore everything that we learn on the contrastive learning, but we still want to do augmentations of the same image, so just the input is the same. But here we define two networks, the student and the teacher. In the case of SimCLR, this is exactly the same network, so there is no difference. If you remember on the loss, it was the features Zi and Zj in the loss function come from the same model, so there's no distinction between student and teacher, unlike now. And here we have to decide which loss function should we use, what teacher should we use. I gave you the answer. What will we use as a teacher? Now that there is no pre-trained teacher, what's the typical strategy? No? We use this exponential moving average of the student weights, of the parameters of the students, will act as a teacher. Even though it's not like a real teacher, as in knowledge distillation, but it's pre-trained. It's like a dynamically built teacher, like a mean over the different student weights over multiple iterations. And then the question is, what loss functions to use, how to make the student outperform the teacher, and so on. So, how to build a dynamic teacher? We take the exponential moving average over the parameters. This hyperparameter alpha is usually 99%, and the larger the alpha parameter is, the more we upweight the previous mean and downweight the current iteration. So for the current minipath, this is the update from each iteration for each minipath. Any questions here? Yes?
So actually there is no teacher network, but we are just establishing
we
pseudo network.
We call the teacher, the dynamic teacher, is an exponential moving average over the parameters of the student. Yes?
What is some typical value for alpha?
99.5
So the teacher stays almost the same.
stays almost the same. The parameters of the teacher stay the same, but the information the teacher sees is better, so he can probably have some better prediction. But there is this dynamic. I would like you to understand that this dynamic, that both networks are improving. The teacher is improving because the student is improving. I also have some plots regarding that. So you have to imagine that both networks improve. Otherwise, we cannot have this idea of dynamic modeling. And this relates to some literature. I have some references that says that model averaging or mean teachers tend to show improved results, and there are different applications in other machine deep learning domain, like reinforcement learning. Some colleagues of mine told me that this idea of exponential moving average is like produce much more stable results. Okay, I covered this one. And we also already saw that in the case of this momentum encoder, MOCO. So exponential moving average, momentum encoder, momentum update, everything is the same. It's just the previous equation, the exponential moving average over the parameters. Just people call it with different names. So we also saw that here, where we have this dynamic set of keys in the previous lecture, we also need to have a dynamic version of the encoder, otherwise this method didn't work. So a dynamically built teacher is enabling us to do much more consistent and better predictions. This is like the bottom line. And this is the dynamic that I try to explain. Yes?
Okay, we are going to take some averages, but if the teacher is larger network, right?
It's not a large network so far.
Not larger, it's the same size.
In order to apply this formula,
Yeah.
both models need to be identical in terms of their
I was going to
architecture.
ask, what if it was bigger, how we are going to take the average to the larger group, and they are the same size?
No, this would be knowledge distillation. So I'm transitioning from knowledge distillation to self-supervised learning. So now the teacher is the identical architecture, randomly initialized, exactly as the student, but it's updated using this EMA. And this is a reference that shows that this technique produces improved results. So this is the dynamic that I was trying to convey to you. So even though we start with two models, we give some small advantage to one of the models, so the teacher, or even some initial small advantage in the prediction, which the student can use this type of supervision, this signal, to copy its predictions, because the teacher sees more information. But in the end, only the student model is updated with back propagation. Like if we break it down in 3 steps, for each mini-batch, for each iteration, only the student is improved with gradients. So with back propagation based on the loss function. I haven't talked about the loss function so far. And then in the 3rd step, these 2 steps is happening for each iteration, we update the teacher. Okay. Any questions about this dynamic? This is what we call self-distillation with these teacher models. Yes?
So at any point, if the student gets ahead of the teacher performance-wise, even after doing
After training.
Yeah, or after doing the exponential moving average and updating the teacher, it's still...
I have some plots regarding this dynamic, but they
Yeah.
both improve.
Yeah, the question is, do they always improve like somewhat symmetrically? Or at one point if the student is just much better than the teacher, would you maybe just switch roles? That you say like, okay, the student is far ahead and we're just gonna swap now, and now the student is the new teacher, and...
Yeah, actually the student, it really depends on the specific method. We have to talk about specific methods, but very generally, the student never gets significantly better. It does that both networks improve, and with this, this parameter alpha that controls how much the teacher is updated, it determines how fast this involvement happens. So with this hyperparameter, of course, if you set alpha to 50%, it will be very unstable, you know, in the beginning. But even, you know, from an alpha of 99% to 98%, this equilibrium of this dynamic would be even much more unstable. But the lower this hyperparameter is, the faster the training happens, this dynamic. So there's a connection between this hyperparameter and this dynamic. But we'll see this in practice. But for most of the approaches that I'm aware and I will present today, after training, if we want to use the representations of these two models, we use the teacher. So we'll talk about two main approaches, two main papers. So this one is called Bootstrap Your Own Latent. Latent means basically embedding space or representation space, or in short, the abbreviation is BYOL. So here there are many things happening. So far this part is exactly the same as SimCLR. We have this pre-trained backbone, we have this projection head, and here we will compute the contrastive loss for without stopping the gradient and everything. So here they do, let's say if we use SimCLR as a baseline, we perform three changes. First, we have this this EMA. So this equation, again, exponential moving average over the parameters, both for the projection and the backbone. Second, okay, yeah, of course, the teacher has access to more information. Third, the teacher is not allowed to learn. So here we could do output.detach or with torch, no gradient, titles, whatever. And we have the projection. We have this output here. And the third or fourth change is that they add another MLP. So exponential moving average, a second MLP on the student side, and stop gradients. So this is the first method. Sorry, yes?
Yeah, you said this upper part teacher has more access to information. This is because the transformations?
Yeah, we can define that if, let's say, random crop, that the student can see
Origin image.
from 5% to 30%, and the teacher can see from 30% to 100%.
Okay,
This is what we will do in the exercise, but I think in this work they just took two random crops of the same size. But it's just that I want to give you this indication of the advantage of one of the models. And even starting from random initialization, they saw some initial improvement in this dynamic. This is not the latest approach, but this was the first one that showed that we can do directly self-supervised learning without relying on negative sum and contrastive loss. What is not shown here is here we have L2 normalization, and here we have the mean square error cosine similarity as we directly optimize this objective, which would collapse in the case of SimCLR. Okay. And another thing is that here they also, since they load this data in the memory, they also switch the data. They perform forward pass and then they calculate the similarity and then use the average of these two losses. This is a really common technique.
And why is the second MLP on the student side?
We'll talk about that. The short answer is that if you remove this component, if you remove this component, this stop gradient, and you enable gradients here, this will collapse. The same for this MLP, and there are contradictory opinions to whether this is necessary or not. In the initial work here that was published on URIP, they say that this is also the third component that doesn't let the model collapse, but later some people remove this part and the model didn't collapse. So the stop gradient and this the second MLP, this creates like this asymmetry. So so if this doesn't exist, it would be an identity, and this would lead to collapse. And this is, since it's randomly initialized, it will never have the identity as an output, in the beginning as it's trained. And the short answer is that these two components enable you to avoid collapsing all the representations to one thing, so all the similarities.
Is it a bit like the centering step that you have in the DINO paper?
Yeah, we'll talk about that. Partially, they achieve the same outcome, but with different ways. Another very tricky component is that inside these MLPs, so we saw that MLPs like linear layer, activation, linear layer, so typically 2 layers. There is also a one-dimensional bus normalization. So even though these two representations only refer to those 2 images, and there are no negatives, let's say, in the loss function, some information regarding what's happening on the mini-bus is incorporated inside these bus normalization blocks here. And there are many works that removed, again, contradictory opinions, but if you remove this bus normalization inside these MLPs, this model will collapse again. There are cases where it can easily collapse. But insofar there is no theoretical work, unlike SimCLR, but it worked. It worked. I don't have the results. So the first component is again the exponential moving average that slowly evolves the features. We already answered this question. The main components are here. You can see on the table they try different combination, and in these 3 scenarios there's usually only one difference. So here they remove the target network. So the target network in their paper is this additional MLP that's called predictor. Collapse. No, predictor is this one. Target network is the teacher. So in the beginning, here they remove the teacher, so the exponential moving average, collapse. Here they remove the second MLP with an exponential moving average. So compared to this model that worked, only one difference, collapse, and then both, and then collapse again. Any questions here? So the asymmetry refers to the additional MLP that's happening here, and not theoretically, but in practice doesn't allow the model to collapse. And this is what they write in the paper, that the teacher is not updated with respect to the loss function, and this kind of gives some intuition why it doesn't collapse, even though there is no overall understanding, theoretical justification. Any questions here? Okay. So far, let's say there's no advantage between the two augmentation pipelines. You have an image, you have two augmentations, two views, you create two views. You pass this information from student and teacher, then their corresponding projection, the first MLP. For this one, you have another MLP. Then you do L2 normalization, which is basically cosine similarity or mean square error. After L2 normalization plus mean square error, which is equivalent to cosine similarity. Any questions so far? Okay, no. So the conclusion here is that even though without explicitly requiring big batch sizes and negative samples, we can train by reconstructing the features from the teacher model, which is the exponential moving average, and learn much better representations at SimCLR. Second, even though we don't require negatives, this method that I presented called BYOL is still sensitive to the batch size as SimCLR, but in much smaller batch sizes. So you can even train this model with a much smaller batch size. So it's less sensitive to the batch size, but it still requires a sufficiently large batch size, like 512. Yes?
Negatives, what do you refer to negatives?
So negatives in the case of the SimCLR loss is the denominator. So basically all the similarities that do not correspond to views of the same image. Okay. Even though we don't really know so far, at least from the theoretical perspective, why collapse is avoided, we still need the batch because, as I explained, there are some modules inside the MLPs, essentially batch normalization. Maybe it would be nice. Okay. Does everybody know how batch normalization works and why we get this information from the whole batch? So we have a model. Okay, let's discuss the case in both a convolutional neural network and an MLP. So if this is a convolutional neural network and this is an image, what is the same here of the output? So we have batch size times some spatial dimension, let's say 8. So this, in the beginning, this is a CNN. So the original height and width doesn't correspond to this height and width. Of course, the spatial dimensions are reduced, but they are still there. So each convolutional layer lightly reduces the spatial dimension and increases the channels. Let's use this format. Let's say I will use this notation to distinguish from the initial spatial dimensions. Here we have batch size, 3 channels necessarily because we are talking about natural images, and then 8, and then width. Okay, how do we leverage batch information for batch normalization, and what does it do? So batch normalization of Z would be okay, let's use beta. So here we have some first order statistics, the mean and the standard deviation, that are computed from this tensor. Okay. So the question is, which dimensions we use here to compute these means and standard deviation? Of course, if we use everything, it's a single mean, but here I have the index of C, which means that we only take the average over the bats and the spatial dimension. So if we have here 128 channels, we have 128 means. So I will shortly write bat size and width divided by So here we get, since we don't take the average over the channel dimension, so basically here we allow each channel to have different means. So we don't want to mix information from these different channels from the convolutional neural network. This common technique up until the latest years. So this M of C and this standard deviation is computed respectively. This is C capital. So they are vectors, and each dimension has each channel has its own mean, and these are the same shape. They have the same shape. These are just trainable parameters. So based on this mean and this standard deviation, we use the information from the bats itself inside those blocks. So these two blocks, okay, the backbone, if it's a ResNet model, it also has some Bayes normalization. But even if you remove the Bayes normalization from here, the model still collapses. And this is how the notion of negatives is injected, but it doesn't happen, it happens implicitly. So we don't really have a loss function that has any negatives by itself. But in order for these two representations to be computed, this Q of Z and zeta, these two representations are dependent on the Bayes normalization here, and thus there is some connection to the mini-Bayes. Is that perfectly clear now? Any questions? Okay. The last part. So now we'll talk about specifically, I think 2 years later, after this initial approach called BYOL, that was proposed from Facebook AI research called DINO, distillation without labels, with no label, and how they managed to adjust the previous method. So instead of having a second MLP here, they modified the teacher side this time. But both approaches just try to create this asymmetry to avoid collapse. Because if you just exclude all these parts, the model is going to collapse. There will be like one representation all the time for all the inputs. So we remove this MLP, that was called predictor MLP. And the second thing, which was very, very counterintuitive when this paper came out, was that instead of staying in the similarity between features, what SimCLR was doing, what BYOL was doing, even with or without negative samples. In any case, both approaches worked on similarity of positive pairs. And now, we, let's say, try to classify all the features in some sort of classes. Yes?
How to choose the number of classes here?
Yeah, we'll talk about that as well. The short answer is some over clustering of the, like some multiple of the real number of ground truth classes. So if you have like 100 classes, some multiple of it. This is the short answer. I was about to ask the same question. So here, instead of having an MLP or whatever network and maximize similarities in the feature space, we have a softmax, which means that we need to assign features to classes. So this is how you can go from BYOL, which is the previous method, to what is called DINO. So first, you need to remove the predictor here. Second, you need to add cross entropy instead of mean square error. Again, mean square error with normalized features is exactly the same as cosine similarity. I will write it down here.